How many of you have tried to open a live oyster? And how many of you lost that battle? A few. It's not your fault. You just tried to overpower one of the most extraordinary mussels in the animal kingdom, probably with a butter knife, or possibly with a butter knife. Tonight I want to show you what's actually inside that shell, because once you know, you'll never eat an oyster the same way again. I'm Margo, and I farm oysters in Jakolof Bay with my husband Frank and my son Logan. Thinking about this biology is basically an occupational hazard for us. When you eat an oyster, the only true muscle you can see is the adductor muscle, and that's this white disc right here. It's actually a small part of the animal, roughly 5 to 10% of the meat, and the rest is gills, mantle, digestive tissue, and seasonal reproductive tissue. But that small muscle does something unusual. The adductor isn't just one kind of muscle, it's two. There's a fast twitch portion that snaps the shell shut when the oyster senses danger, and there's a specialized catch muscle, and the catch muscle can lock the shell closed for hours, even days, while using almost no energy. Human muscles fatigue and fail. That's how muscles work. The oyster's catch muscle just latches. It's like a bicep, more like a bicep than like a deadbolt. It's less like a bicep and more like a deadbolt. That's why a fresh, healthy oyster is so difficult to open, and that white disc tastes slightly sweet because it's rich in glycogen. Now look at the shell, because this is where the animal becomes something closer to a materials engineer. The thin layer of tissue lining the inside of the shell, this part all along here, and here it's folded back. That tissue is the mantle, and it built every bit of that shell. That soft stuff builds hard stuff. The mantle pulls dissolved calcium and carbonate ions directly out of seawater and crystallizes them into calcium carbonate, essentially chalk. But it organizes that chalk into an incredibly precise structure. The inner layer, the slight iridescent shimmer you sometimes see, is nacre, or mother of pearl. And at the microscopic level, it's built from tiny mineral plates stacked with organic layers between them, forming a composite material that's dramatically tougher than pure calcium carbonate should be. Material scientists study nacre because the structure is stronger than many synthetic ceramics. Your oyster is doing nanoscale materials engineering continuously from seawater for its entire life. In a very literal sense, oysters are built from seawater. And a thick shell tells you something about the environment it grew in. Productive water, good food supply, enough stability for the animal to keep investing energy into its armor. So here's where the biology becomes flavor. You can actually taste both of these systems at work. That sweetness, that's the adductor, glycogen from years of holding on and strong currents. The brine, the minerality, that complex finish, that's everything the mantle filtered out of the water to build the shell and keep the animal alive. And the deep savory note, the umami, comes from the nutrient-rich tissues where the oyster stores and processes all that plankton and prepares for the next cycle of life. So when people say an oyster tastes like the sea, they're not just being poetic. They're describing the chemistry of a specific place, filtered and concentrated by living animals over 3 to 5 years. At least here in Alaska, it's 3 to 5 years. So our oysters go in Jakolof Bay in some of the strongest tidal currents in Alaska. Those currents are why our oysters' adductors are well developed and why our shells are strong. If you want to taste what I just described, unfortunately, it's not our oysters tonight, but fortunately, it's Eric's oysters. He's in the back also. But if you want to taste our oysters, we harvest to order, and we do pop-ups in Anchorage. Find me after, and I'll get you on the list. That's all I got.